In Chapter 6, we're going to take a look at two different sections to kind of highlight the last two columns in our formula sheet. These columns are going to be based on what we call sampling distributions. So let's take a look at what we mean by this. As I state here at the top, in Chapter 3, we learned about probability was helping us measure the likelihood of certain events happening randomly. And randomness is ultimately a tool. Random happenings are unpredictable in the short term, but in the long term, there can be some patterns and some regularities. This is what probability is all about, helping us understand what happens in the long run. So what we're going to be doing here is to try to understand that there are some other interesting random variables that we can make use of here. So a sampling distribution of a statistic is a probability distribution for all possible values of a statistic that's computed from a sample size. So when we talk here about a statistic, remember this is some value that describes a sample. So one of the statistics that we could use, one statistic that might have values that change from sample to sample, is actually going to be the sample mean, which of course we know has the symbol of x bar. So what we're going to look at in this section is how the variable x bar acts as a random variable. That is, its value will be determined by chance as we take different samples. So as we see here, the sampling distribution of the sample mean of x bar is a probability distribution of all the possible values of the random variable x bar when I compute those from a sample of size n, and that sample comes from a population with a mean and a standard deviation. Now we're going to try to get a sense of what we mean by this, but first I'll go ahead and look at the formula sheet here to get our bearings on exactly where we're at here. What we'll see is that we're going to be working again here in section 6.1, and so that's associated with the fourth column on our formula sheet. And notice specifically right here at the start is that our random variable is no longer just a capital letter like an X or a Y or a Z, but instead it's a very specific symbol that we've used before in this class, the symbol X bar. Remember that X bar is the symbol that we use to represent the average of a sample. And so this column is all about answering questions related to finding probabilities about what a sample average will be. So anytime that we come across a question that's asking something like, what are the chances that the sample average will do something, we know that we're going to be working in this column. Now in the next section, we'll take a look at another sampling distribution with another new fancy symbol that we have yet to define. But again, that's later for 6.2. So now that we kind of have a loose idea of what this fourth column is all about, let's go ahead and try to take a look at example 1 to kind of see how this all comes together. So as I state here, how exactly do the values of x bar behave in a given experiment? So let's consider the following scenario. Now, let's suppose that I have brought a deck of cards with me to this actual lesson. Now, if we were in the classroom, I'd actually have a deck of cards, but here I'll settle for looking at a deck of cards online. Now, each deck, in case you're unfamiliar, contains 4 copies of cards that have values of 2 through 10. And then there's a card that's referred to as a jack, a card that's a queen, a card that's a king, and a card that's an ace. So I'll quickly go ahead and take a look at what those cards look like. So here's a picture of like what a standard deck of cards would have in it. I can see here that these cards at the left are aces. They have one symbol on them, but oftentimes they're regarded as like the largest possible value. In our case, we're going to count them as a value of 1. And then I have other cards that have different numbers on them, and then I have these J for jacks, Q for queens, and K for kings. So this is a standard deck of cards. You'll see that it's also kind of separated out into different colors. There are red cards and black cards, but there are also cards with different shapes on them. So these up at the top are clovers, or what's more commonly referred to as clubs. You have spades, hearts, and diamonds. And so we're going to be thinking about selecting cards out of a deck like these. Now in total, there are 13 different values of cards per suit or per symbol that's on them. And so in total, there are 52 cards in a total deck. So what we're going to do here is we're going to think about assigning values to all of the different cards. Let's pretend that we're going to give the jack, queen, and the king a value of 10, and we're going to give the value of every ace a value of 1. And so what we're going to try to do here is to think about kind of how the different values of cards are kind of spread out throughout the deck. And we're going to create a frequency distribution of the values of these cards. So let's take a look at the different values that we could have. We just said that we're going to give cards values of 1 through 10. And we want to now figure out how many cards in the deck would say have each of these values. Well, if I look at the deck again, how many of the cards in here would have value 1? Well, based on what we just said, we said that aces would have value of 1 because they have one symbol on them. So there are 4 of those cards in the entire deck. How many cards in the deck would have a value of 2? Well, again, if I go back, there are 4 2s. There are also 4 3s and 4 4s and 4 5s, all the way up to 4 9s. But remember that we said we're going to give each of these other cards with the pictures on them a value of 10 as well. And so there should be 4, 8, 12, 16 cards that we're going to give a value of 10. So if I was to fill this out down here, I can see that I get 4 cards of every value except for 10s, and 10s are way more frequent right now. So I could start to answer a question like part B. What might be a possible shape for a distribution of these card values? Well, you could try to imagine almost creating like a bar graph or something like that for these different categories. And what we might see is that pretty much all the bars are going to be at the same height, a height of 4. And it's only this last bar that is something different. So I don't really have a good shape for something like this, but maybe I'll state that the distribution is almost uniform. That's at least probably the best I could do to describe this. I mean, it's almost the case that all bars would be the same height or that every class is the same frequency, except for this stupid last class. It's so close. Okay, well, if this is the case, if this is my population and I'm going to start to grab X bars, that is, I'm going to grab sample averages, I'm going to try to come up and conduct a particular experiment. Let's take a look at what we have. On the next page here, I'm going to ask that we go ahead and imagine what it would be like to take a sample of 5 cards from a deck of cards and compute the average card value out of the ones that we select. And once we've done this, I'm going to go ahead and record the results in this stem and leaf plot over at the right. So let's take a look at another online simulator that can allow us to simulate taking cards out of a deck. So you can see here, I'm back to my deck of cards, but I'm going to go ahead and move over to this next tab. Here you can see I have a bunch of cards that are face down, so they're hidden. And if I randomly pulled out 5 cards, I can see I get some different face values. Now in this case, I could go ahead and calculate out an average for this. Notice that I'd have to add up all of my different values. So I'd have something like 10 and 10 and 10. All these cards are worth 10. And then a 6 and a 3. I think that's a total of 39. And so what I could look at here is the following. If I grabbed an X bar, and I'll put a 1 on it because it's my first one, I got 39 total value out of 5 cards. And if I was to go ahead and crunch this out, what I could see here is that this is going to get me a value of like 7.8. So I'm going to record that value over here in the table. 7 is going to stand for the whole part, and I'm just going to put down the decimal value of the 8 over here. Now, notice I could do this a whole bunch more times and get a lot of different X bars every time I draw new cards. I could go back and say, do it again. And this time when I do it, I can see I get a different value. Here I get 10, 20, 30, 39, 42. So here I could say I get 42 cards out of 5. And so that's actually going to give me a value of 8.4. So I could leave the 8 and put a 4 down here. Now I could imagine continually doing this like a whole bunch of different times. And what I could start to see is I could start to create some sort of like a histogram that might appear over here on the side. Something like a histogram in the stem and leaf plot. And what I could start to see then is what things begin to happen a lot and what things don't seem to happen a lot. Let's go ahead and just click out a couple more values of this to see if we can understand what sort of patterns might begin to emerge. Okay, so here I'm going to have, let's see, this is going to be 17, 24, 31, 41. So here for my X bar number 3, I got 41 on 5, so that's an 8.2. So I can see that some of these values are going to repeat. I'll try this maybe just 2 more times total, to kind of get a sense of what values might begin to pop up a lot and which ones are rare. Here, I can get 10, 20, 26, 34, 43. So this time I got 43 out of 5. That's a value of 8.6. So I'm going to write 8.6. Last time here, let's see, this time, ooh, it looks like I might have gotten a low one. So I have 9. 9 and 4 is 13, 16. This time I got 21. 21 out of 5. That's going to be 4.2. So I can see that a lot of these different values might be possible, but we're already kind of getting a sort of maybe a hint that it seems like values that are maybe up in this range, maybe values around like the higher, like the 7s, the 8s, I don't know, maybe the 6s, maybe those pop up more likely or more often. Well, it's kind of hard to go ahead and see how exactly this can play out unless I do a lot of individual cases. To help with this, I'm going to go ahead and go back to one of our simulation applets that we looked at the very beginning of the semester. You can see that over here in my simulation applet, I've actually already included all of the different values of the cards in my little scroll box here. And you can see kind of a picture of the histogram that we have, where I can see that most of my things occur 4 times, and then the values of 10 are very, very large. And what I'm going to do is show some sampling options. We want to kind of repeat the experiment that we were just doing. I want to go ahead and select just one sample, but I want to do that by selecting 5 cards out of the deck. Notice, in this case, I would have grabbed a card with a value of 9, 8, 10, 4, and 10. And you can see here that these are where all these cards would be kind of if I line them up on a number line. When I grab that average, okay, the average here is 8.2. And what you'll notice is I can kind of put that value now over here in the picture. So I have a bar that's around 8.2. I could continue to do this. Notice this time I get a value of 8, 6, 10, 6, and 4. That gives me an average of 6.8. And I can put that in my picture. And I could continue to do this a whole bunch of times. Notice that in my picture over here, I'm kind of adding in all of my different samples. So I can begin to see the things that happen a lot and the things that don't seem to happen a lot. If I want to speed up this process, I can also go here and click on the number of samples. Maybe I want to do like 1,000 times this experiment, right? I want to do it 1,000 times in a row. Well, if I do that, I can start to see things that happen a lot. And we can go back and begin to answer some of the interesting questions that we have in some of these later parts. You'll notice down here, can we see any trends with how the values of X bar behave? Well, yeah, we definitely can. If I look at this pattern that's emerging after I've done this many, many, many times, it seems that values from like 6 to 8, maybe 6 to 7, seem to happen a lot. So it seems like values, or we could say here, since those values represent averages, in the 6s and 7s seem to be the most common. It was hard to see that when I only had 5 data points, but after I do this a whole bunch of times, I can start to see this shaping up. Part E. If you use the simulation and repeat the process, like we had just done, what do I notice about the shape of the distribution? Well, remember before it was kind of almost uniform, right, over here, except for this one bar at the side. But now, what kind of shape does it have? Well, it almost looks bell-shaped. So I'll write that here. It appears bell-shaped. Well, what's interesting here is more than it just being bell-shaped, I can see some other sorts of similarities. Notice that over here on the side, if I was to just say, if I was going to pull one card out of the deck, what's kind of the average value of a card that I would pull? Well, if I look at it, I can see that value showing up right here. The average that I would pull would be 6.538. That's about the average card. And the standard deviation is about 3.153. Well, what you'll notice is that if I go over to this picture, isn't the average almost identical? Like it's still in the 6.5 range, but the standard deviation has gone lower. I'm going to continue to look at that interesting connection of the means and the standard deviations as I continue into part F. What seems to happen to the distribution of X bars if we repeated the experiment, but instead of only taking 5 cards out of the deck, what if we did 10 cards? Okay, well, let's see. I'm going to go here and do sample sizes of 10. And if I was to draw samples again and maybe do this a whole bunch of different times, I can still see that values in about 6 to 7 range are very common. I still get something kind of bell-shaped. And actually, if I look over here, don't my averages still almost line up? And notice my standard deviation got even smaller. Okay, what happens if I increase this to, imagine selecting 20 cards out of the deck and then computing an average? Well, if I do this a couple times, I'll still notice that grabbing values from 6 to 7 is very common. And look at this. Wow, the average is like almost perfect, a perfect match right now. And the standard deviation used to be at 0.9. Now it's down to 0.5-ish. So it's getting even smaller. What about if I up to 30? What if I pulled 30 cards out of the deck and I repeated the experiment? Well, again, I can see, wow, I'm still getting this kind of bell-shaped distribution, but now, I don't know, maybe from like 6.3 to 7 is probably the common cards, most common. And wow, look at the averages. They're still super close. And my standard deviation went down again. However, in all of these things, we can notice that the distribution was roughly bell-shaped. We can also see the mean of the X bars was roughly the same as the mean for a single card. And we could also say that the standard deviation of the X bars kept getting smaller as the sample size got larger. So these are kind of 3 interesting connections that we can see here. And what's kind of surprising is that those connections actually can be quantified and organized and summarized into one of our most important ideas in all of statistics, what we call on this next page the central limit theorem. Now, I'm going to go ahead and read over this quickly, but we'll deal with examples and how we actually utilize this and implement this in the next several videos. Let's take a look briefly at what this says. The properties of the sampling distributions of X bar are as follows. The random variable of X bar, notice again it is a random variable. Its value changes and it's determined by chance. But what distribution will it have? It will have a normal distribution or approximately normal, as long as one of 2 things are going to happen. Notice that the distribution that I had here was kind of almost bell-shaped, but it wasn't like perfect. Maybe it was getting close to being roughly bell-shaped. But once I have a sample size that is large enough, that is, I select numbers of items that are 30 or greater, 30 items or more at a time, and then compute my X bar, I can guarantee a normal approximation or an approximately normal a normal distribution or an approximately normal distribution. Or if it's the case that the population from which the sample was taken is normally distributed, then I'll know that X bar will also start to fall into a normal distribution. So if at least one of those conditions is met, then I can also see the following connections. Notice here the importance of our subscripts really jumps out. The mean of our X bar picture, that is the mean that we're getting right here, the mean for our X bars, for our sample averages, will actually come out equal to, completely the same as the average of X, which would be the average for a single item selected. So the average over here and the average over here, if I continue to take samples on and on and on and on and on and on and on forever, they will actually become perfectly the same. In addition to that, the standard deviation for my X bar picture is not the same as the standard deviation for the other, but it's related. And it's related by saying the old standard deviation would always be divided by the square root of the sample size. This might explain why as the sample size continued to get larger and larger and larger, the standard deviation of the x-bars kept getting smaller and smaller and smaller. If I throw a bigger number under here, this right side becomes a much smaller value, meaning that the standard deviation of the x-bar becomes much smaller. It's also then possible to find z-scores of x-bars, so I can figure out like how far away are certain x-bars from the typical x-bar. And I do the same thing. I take my values, subtract an average, divide by a standard deviation. And I can simplify this formula down a little bit by plugging in these other values in place of the key variables. So we'll take a look at how this all plays out in a specific example and a set of calculations in the next video.